All right, so biological data insight and modeling is the theme. There's the abstract. So DataModeler's been hanging around for quite a few years, doing a lot of industrial design, analysis, some sports teams, other stuff. But in the last few, we've gotten into the biological space. And it turns out that omics is the theme. Maybe. So you got proteomics, genomics, lipisomics, metabolomics, and it's just cranking up the number of variables that you're looking at. Still in the medical space, they're not having a lot of patients. So now we're getting to these sort of super fat data sets. We're engaged in a few NSF studies doing analysis, but today we'll be looking at data from bone regeneration, because in terms of bone healing, you want to be able to detect early on that you need to have an intervention if you're not progressing properly. This particular data record, reasonable. Immune response, so this is metabolite data. This one's pretty tough, 8,000 variables, right? And only 20 patients. We're trying to identify the biomarkers that are going to be indicators of the immune response. Cancer vaccine's a near and dear one to my wife's heart because her sister died of glioblastoma, brain cancer. So she's done quite a bit of work with this. Basically, what the cancer vaccine approach is you've got it's CAR T therapies. So you want to train the immune system to recognize the cancer cell, because we have mutations all the time in our bodies. The immune system detects it, cleans them out. Some of you get cancer when the immune system says, okay, you're friendly, and they can run sort of amok. Now, the idea is for the CAR T therapies is that you want to train it, but the problem right now is growing the cancer cells doesn't scale well. It's very expensive, millions of dollars to treat one patient. That's not hitting the overall need for cancer. And then single cell multiomics is just basically you can take the same cell and measure over and over again. So you wind up getting a huge data set, but a limited number of patients, and it's noisy. So you have to do sort of special things in that space. I am not going to do anything with the DataModeler GUI other than to say that it is a thing of wonder. I went for many years as being sort of a command line notebook bigot, and I was sort of forced into getting the GUI built. But the reality is, when you're dealing with this sort of data sets, you're very interactive. You're taking your data and focusing. You got a huge haystack. You're just trying to make that haystack smaller and smaller, and figure out what really matters. And it becomes an interactive thing of doing a thing. What if I want to go look at the data, and you're just sort of bouncing back and forth, and having something that's file driven and supporting that workflow is a good thing. So we've got this data. So what do we do? I mean, just before we get into this, is sort of general to DataModeler. If you've got big data sets, you have ordinal GP, basically subsetting the data, figuring out what's going on, and because you can evaluate a model as a good or a crappy model on a subset of the data. You don't need infinite precision in the initial stages of this sort of evolutionary process of modeling. Missing data, very common approach that we do, is because what we're going to do is we're going to look at it, we're going to develop algebraic models on explicit variables from the data. So unlike a neural net, which assumes every variable matters, we're assuming a handful matter, and we're going to throw in a constraint that the variables that we use have to cover the data set to a reasonable extent, 75%, 90%, whatever you specify. But this is how we're able to handle missing data. So we're not doing an imputation stage. Model support, if you've got a handful of records, you don't allow 27 variables, right? So we have a requirement that no more than 20% of the defaults, you can have the number of variables, the number of basis sets, sort of top level additive terms, can be no more than 20% of the number of data records. And you can, sometimes you want to specify that a little lower, just be cautious. We have the issue when you start dealing with small data sets that we just have quantized data. So we've got interstitial regions in our parameter space. So how do we handle that? Well, one of the approaches is to do what I call robust models. It's just basically using interval arithmetic and guaranteeing that I don't have a singularity in between 1 and 2 and 5. So we have this sort of issue. The other is that you can analyze the models with the ANOVA trim, clean out terms, models that don't at the top level pass an ANOVA test. So the statisticians can be happy with you. And eventually, because we're going to go through and we're going to do this modeling, and it's going to be stochastic, and we're going to have thousands and thousands of models and a handful of variables that we really look good. We're going to build ensembles models, and these give us trustable models. Okay. All right. So data characteristics in sort of the case I'm looking at. Very few records, tons of variables. It's ill-conditioned with correlated variables just as well as having too many. Missing data, we got to only have the ability to analyze the data because people love, if they don't have data, to substitute in a 0. A 0 is not necessarily a 0, right? Sometimes it is, but oftentimes it is. We need to handle that, and if appropriate, convert it to being missing. And then quantized is a big issue when you only have a little bit of data. So what this is here is a snapshot of the metabolite data. So we've got 8,000 variables, and if I look at the models that are developed, I mean, this is not something any statistician would propose as a model, right? I mean, the evolutionary process identified these things, and they're passing. I can do an ANOVA test on it, and it's legal and it's accurate, and it's just what this building blocks. But what we're trying to do is, in the early going of this, is focus things down and figure out which variables matter. And occasionally, once we figure out which variables matter, we figure out which ones are the most controllable. But our whole assumption in this process is just really what makes a good model. It should be simple, right? We're assuming a handful of variables matter, but we want it to be a small, compact model, and it wants it to be accurate. And that is the evolutionary pressure that we're applying. And in this case, we have 1,000 models that we did out of the initial search. So if I look at those 1,000 models, first, one of the questions I want to ask is how many variables do I need? So someplace, 2 variables gets me to better than a 90% R squared. I mean, that's, for a biological system, that's going to be pretty attractive to me, right? Don't chase R squared. That, I guess, is my theme in this. But what we're doing here is we're explicitly exploring that complexity accuracy trade-off. And because of that, because of the ability to do complexity control, we can do things like build ensembles and have trustable models. So, I guess the other thing here is what you notice. Now, this particular variable combination map is showing that for all of the models in the data set with 2 variables, what are the combinations of variables that are there? We see a very strong presence of TNFA. I can't read it, but it's 93% of the models of that set. So we've got combinations. We can start to see sort of dominant variables. We're doing sorting. All right, so we're starting to get a feel for about how many variables we need, and say, what variables matter? Now, the we can really basically do three things with this. So we've got 1,000 models, and we look at our population models, and we say, well, which variables are most prevalent, right? So what's variable presence? Because presumably, if they're in a reasonable fraction of the good models, then they're useful variables, and they've percolated up to the top. We can look at combinations of variables and say, this particular group of 3 variables produces good models, and that's a useful thing. Maybe I want to go do some modeling with just those 3 variables. And then we can look at associations, which variables play nice with one another. Oh, geez, sorry. So looking at variable presence. So what this is again, continuing the immune system response with the metabolites and all. A lot of variables went in. Only a couple hundred were even in the interesting models that we sort of selected to do it. Now, the thing is, it is a needle in a haystack problem. We've got of possible triplets, 10 to the 11th possible triplets, but over the course of my modeling of only done millions of models that have been explored. So what I'm gambling is that a variable that's come through in this stage is something that is interesting. I want to do a lot of modeling before I make a strong conclusion, and let things happen and be sort of slow as I try to make this haystack smaller and smaller. One of the other neat things on this is this, this variable right here was in over 10% of my models. So this is a variable that's pretty cool, 5098. If I look at just strictly linear correlation, see how good my fine motor control is. It's in 3.7%, just strictly from a linear standpoint. It's not something that would pass threshold if you were doing an initial cut based on correlation, okay? So
what is the response variable that you're using?
No, it's a score that they have for functional effectiveness. I don't actually know how it's calculated. In this case, it's a continuous variable. And then variable combinations is sort of obviously that if it works, maybe it's worth doing. You get into situations where I'm looking at variable selection, and they're all metabolites for this particular situation, but you can have variables that are controllable, variables that are observable. Let's focus in on the ones that are controllable. Okay, associations is the other thing that we care about. And that's just basically which variables like to belong with other variables. So I've gone through, and this is sort of an association plot. If I look at the sort of dominant triplet, we see that it's not really highly linearly correlated. We can look at the coverage of the design space, and they tend to, observation is, that tends to cover the design space better. So there's sort of maybe an analogy to mutual information that's an evolved property. Meta variables are sort of building blocks that can sometimes provide insight into mechanisms. Ensembles are what really is the neatest thing out of this game. So we've got a bunch of models. We've got, so we've now down to 3 variables that we're going to use, or 2 variables that we're going to use in our ensemble. And we've gone and done some modeling, and now we've still got 1,000 models that we could choose from. How do we choose the model? And the problem with the model is the model wanders off to Never Never Land, and you have no clue of what's going on. If you build an ensemble, the Ensemble has a special property that it agrees where there's data. Otherwise, they wouldn't be good models, but we're going to choose them based on their diversity. So if we ask them to extrapolate, if they go into new regions of parameter space or the system goes through a different change, then I could detect that. Okay, so this is really neat stuff. Now, it assumes, of course, in any data-driven modeling, that your actually data covers the design space and a variable that's real important was not held constant through the whole thing. Okay. But it gets around the issue of, I mean, the reason we can handle these 20 data records is we don't need to partition it to test, training, and validations, because we've got two things. We've got explicit complexity control, and we can use the power of the crowd to give us an overall behavior. So we get that trust metric. So this is just some bone regeneration. So this is a problem of if the military is funding this one just because of war injuries, so you get people with fractures and such. So you're trying to get the bones. Man, the idea is that can you early on predict what's going on and do necessary interventions, but if we're going to take the metabolites out of the patient, which ones are triggers that's progressing well or not progressing well, or indicators rather. And here I just, there's 4 different ensembles and different combinations of variables. They really, from my perspective, they're all roughly the same. So if I can chase R squared, and these 4 variable ensembles get, a little bit better, but from a practical standpoint, the ensemble performance doesn't really differ a whole lot. But what we see here, if you look, leptin at week 9, if we hold the other variables constant where those green dots are, that's the reference point for this graphic. If we move that without changing anything else, we're going into an unknown region of parameter space. And so our trust metric expands. Okay, so this is pretty cool stuff. Data cubes and summary statistics. So this is the single cell RNA where they've got let's see, 8,000 experiments, but they only have 20 patients. They basically have the same data record over and over again. So we can model on the metabolites that they measured out of this, or the features that they measured, the RNA actually out of the single cell. Or we could do summary statistics on each group of patients, and maybe that tells us more that, does the spread, does the interquartile range of a particular RNA matter, or does, so we can actually get more insightful models. But doing this one's sort of neat because it winds up, that there's a huge gap in the response region. And this is the problem with dealing with small data sets. So there's interstitial gaps. And then trade-off analysis. If I have, and this is the case getting back to the cancer cell stuff, where you've got total live CD4 and total live CD8 cells. So the CD4, if memory serves, if I'm correct, is controlling the immune responses, how aggressive your body is in terms of reacting to the cancer. The CD8's a modulatory T cell, so it damps things down because so you don't get a systemic reaction as and kill yourself in the process of curing yourself. Okay, so all right. So conclusion is, what we're creating out of this process is a white box model. It's interpretable. We can build these ensembles, which is going to give us the trustability factor. The humans in the loop. I mean, the assumption is that a handful of variables matter, but I am responsible for deciding which handful makes sense. Which does this agree with my mechanistic understanding of biology? It's essentially nonlinear models, but this is an issue here because everybody knows biology is linear, right? but it's the other thing is we're not doing hyperparameter tuning. We're not tweaking out the yin yang to get an answer, which is just sort of falling out for us. So very unique capability for this class of data. You know, it's a good capability for, you know, all classes of data that sort of spreadsheet style data sets of, you know, 10, 20,000 variables and, you know, less than 1 million records. But for this particular super wide stuff that we're running into in the biological space, I mean, it's really the only game in town, because partial least squares get you, you know, maybe to 50, 100 variables. Lasso's doesn't do anything for you. Obviously, you don't have enough data records to do, you know, almost anything else. You've got to really isolate down to the factors that matter. So that wraps it up. And thank you for not being out on that bus that's sitting there waiting for you. And if anybody's got a question, I'm here.
So I assume I can later, but any kind of dimension reduction you do normally transpose this 20 by 10,000 matrix. Am I correct? You have like super wide table,
Right,
with say 10,000 variables and 20 rows.
right.
So if I want to do any dimension reduction, I kind of
No, you do it directly. You do it directly, because the idea is that we're going to do what we're going to do is we're going to say that, or we're going to allow, we don't know which ones, but we're going to allow 3 variables into our models. So you're doing a dimension reduction to 3 variables explicitly.
You're selecting, okay, yeah. I was talking more like matrix decomposition type of algebraic dimension. Then, okay, right, my point is what, imagine I do thin singular variable decomposition on the transpose matrix. Then I can group this 20 people into some.
Right. So partial least squares, I mean, that's a partial least squares regression is essentially what you're talking about, the decomposition. You look at the dominant singular value and you say, you know, which terms are dominant in the dominant singular value that contains, you know, and how far deep do I go into the energy? Gives you a linear model. That's a good thing. If, you know, so here we're not constraining to linearity. And if you look though, you know, the trade-off curves they're not linear, right? I mean, this is, you know, these are biological systems. They're not linear. So to impose a linearity constraint isn't, from my perspective, valid. Now it may, you know, it does work. I mean, the whole point of linear modeling is that it works. It's, you know, in engineering solutions, it's great because we can make approximations there. So, okay, I have been told to sit down, shut up, but I'll still stand here if anybody cares about it. Otherwise, anybody who's not interested, just, you know.
Another kind of question that maybe if I discretize this, and then instead of looking for correlation, the variables themselves, I'm looking for association rules between the discretized ranges.
Right. Oh, so I mean, you can do a mutual information thing. That's very computationally heavy.
Right.
So it's, I mean, the scale of the problem is such that a mutual information approach really doesn't scale into it. Okay.
So Anton asked this question. When I see 10,000 variables and cluster them. So instead of 10,000 variables, he has 10 clusters. And then he was going to use each of the clusters to try to predict response.
Right. So, I mean, there's obviously, you get highly correlated variables. They're
highly correlated variables makes, you know, ANOVA meaningless. You know, as soon as you let in the first correlated variable, the other 7 correlated variables look like garbage.
Right. So what happens, so what's sort of neat out of this is that the models that are developed are, you know, they'll pass, even though they weren't told to, they'll pass the ANOVA test. Okay, because it's basically, there's a focusing in on combinations, you know, if two variables are highly correlated, the energy basically gets consolidated into the ones that are most predictive, the higher information value rather than the higher linear correlation. Okay. Bob? I ignore it. In this case, I don't have any missing data, but in general, I just ignore it. And you don't have to stay and listen to me.
You drop the variable, you drop the case, what do you drop?
Well, so remember, you're dealing with explicit variables, right? So what I'm going to do is each model, when it's evaluated, I'm going to look at the variables used by that model, and I'm going to say what fraction of those, the inputs of those variables for that model are completely numeric. And if they're over 75% or over 80% or over 90%, then I'm going to say, okay, I got enough support that I can, despite the missing data, that I can, if it's a high quality model in terms of its R squared.
So that subset of variables, you drop then that 5% that you don't have enough.
Right.
And fit the model
To the available information.
next model.
Yeah.
Different set of
Right. So I mean, in this fashion, you can handle where they're scattered and across the entire data space. Right. Yeah. We don't want to delete everything that's missing. I don't like imputation because I don't believe in it. It's actually viable in this space because if you specify, it's possible to do imputation. The imputation default behavior is just to simply sub each missing one with another record, another instance of that variable, so that at least you're matching the distribution. I mean, so it's an easy, cheap way to match the distribution up. Huh?
Random selection with replacement.
Yeah, with replacement of the numeric ones.